Alternating current fundamentals. Number 4. Capacitors, inductors, and transformers.
In the last part, you saw how alternating current can be represented using waveforms called sine waves. Amplitude and frequency were described. You saw that AC and DC values can be correlated by understanding the difference between peak and RMS voltages. In this video, 3 devices that play important roles in AC circuits will be examined: capacitors, inductors, and transformers.
The basic construction of each device will be investigated, along with their schematic symbols and units of measurement. You'll be introduced to the basic principles behind their operation.
Let's get started. You've already seen that resistors serve the same basic purpose in AC circuits that they do in DC circuits and are used just as frequently.
While the voltage across and current through a resistor in an AC circuit constantly change over time, the Ohm's law relationships among voltage, current, and resistance still hold true.
But the devices you'll see in this video have characteristics that are most fully exploited within an AC circuit. Their full operation relies upon the varying voltage and current that is present in AC.
Let's examine capacitors, inductors, and transformers, starting with capacitors. If you could see beneath the cover of virtually any electronic system, you would find capacitors of all shapes and sizes. Look inside this unplugged radio, for instance. Capacitors can be found in the power supply circuit, in the tuning circuit, and in the amplifier circuit. Regardless of the particular application for which they are used, all capacitors exhibit certain common operating characteristics.
The basic job of a capacitor within a circuit is to store an electrical charge. Let's see how a capacitor is constructed in order to accomplish this.
A simple capacitor, or cap, is composed of 2 metal plates which are conductive. The plates are parallel and are separated by an insulating material called a dielectric. Different types of capacitors use different substances for dielectrics, but regardless of the substance used, it is always within the dielectric that the charge or electrical energy is stored. Each plate of a capacitor has a lead attached to it. These leads are used to connect the capacitor to an electrical circuit.
Let's see how a capacitor functions step by step. First, in a simple DC circuit.
The 2 rectangles labeled L and R at the top of the circuit represent a cross-sectional view of a capacitor's plates. In this case, they are separated by a dielectric made of air. At this point, each plate contains an equal amount of free electrons. The capacitor is in a neutral or uncharged state. But when the switch is closed, the battery voltage causes electrons to flow in the circuit. The positive terminal of the battery will attract free electrons from the capacitor plate on the left, labeled L. At the same time, an equal number of free electrons are deposited on plate R on the right. As plate L loses electrons, plate R gains electrons. Plate L becomes positive with respect to plate R because it has a deficiency of electrons.
It's important to realize that during this process, free electrons do not pass through the dielectric because of its insulating characteristic.
Free electrons travel through the connecting leads, source, and switch only. This forced movement of electrons from one plate to another by a voltage source is known as charging. The electron flow is referred to as a charging current. The applied voltage will continue attracting free electrons from plate L and forcing them onto plate R until the voltage across the capacitor, labeled E sub C, equals the maximum voltage across the source, labeled E sub S. At this point, the voltage across the capacitor has the same polarity as the applied voltage. Current ceases to flow because there is no longer a difference of potential between the voltage source and the capacitor. When the switch is opened, the charged capacitor is disconnected from the voltage source. But within the capacitor, there is a negative charge on one plate and a positive charge on the other, causing an electric field to be developed in the dielectric between the plates. The arrows represent the electric lines of force which make up the electrostatic field. The strength of this field is directly proportional to the potential difference, or voltage, between the plates.
Stop the program and complete activity number 1. When finished, continue watching the program.
When charged, a capacitor can be thought of as a temporary battery because it can retain the stored charge for a long period of time. However, once provided with a current path, it can release its stored energy. Let's see how the capacitor does this within the context of the DC resistive circuit.
When the switch closes, a current path is provided and the capacitor begins to discharge. During discharge, the surplus free electrons on negatively charged plate R flow back towards positively charged plate L. Again, the electron flow is from lead to lead through the external circuit and not through the dielectric. This process is called discharging, and electron flow is known as the discharge current. When all the surplus electrons have moved, both plates become electrically neutral and the capacitor is fully discharged. The voltage across its terminals is 0.
A high voltage or any high-value capacitor can produce dangerous electrical shocks and burns if mishandled. As a student or trainee, you should never handle charged capacitors without the immediate supervision of your instructor. Let's consider the proper methods for safely handling charged capacitors.
Imagine that you find an unidentified capacitor. The best thing to do in order to be safe is to check to see if it's charged with your voltmeter. This procedure assumes that your voltmeter is capable of reading the highest voltage that could exist across the cap. To discharge a cap, use insulated alligator clip leads to connect a high-value resistor across the cap. This will safely discharge it. A cap that is discharged should read 0 volts across it.
Up to this point, a graphic representation of a capacitor has been used. However, this is the actual schematic symbol for a capacitor, which you will find on circuit diagrams. Now that we've examined the charge and discharge processes of a capacitor within a DC circuit, let's take a look at how a capacitor will respond to the changing values of voltage and current in an AC circuit.
Again, a single capacitor will be used in the circuit for demonstration purposes. An AC source voltage with a peak value of approximately 170 volts will also be used. For this analysis, a single AC cycle will be divided into 4 quarters. During the first quarter cycle, from 0 to 90 degrees, the magnitude of the source voltage is increasing. The capacitor charges to keep the capacitor voltage equal to the source voltage. Charging current flows until the capacitor reaches the peak voltage of 170 volts. At this point, entering the second quarter cycle between 90 and 180 degrees, the magnitude of the AC source begins to drop off. Since the capacitor and source are in parallel, the voltage across both must be the same. This means that the capacitor must discharge to reduce its voltage during the second quarter cycle. At 180 degrees, the voltage will be 0 and the capacitor will have fully discharged. At this instant, the polarity of the AC source reverses. And during the third quarter cycle, from 180 to 270 degrees, the voltage increases toward its negative peak of minus 170 volts. As the source voltage increases negatively, the capacitor must now charge with the opposite polarity to follow the source. Charging current will flow until the capacitor reaches the peak voltage of negative 170 volts. During the fourth quarter cycle, the AC voltage drops off, moving back towards 0. And so, during the last quarter cycle, the capacitor discharges to reduce its voltage and follow the source voltage. The discharge current will flow until the source and capacitor voltages are zero at 360 degrees.
Now that you've seen how a capacitor stores and releases energy in an AC circuit, let's look at some important terms associated with capacitors.
The indicator of a capacitor's ability to store a charge is called capacitance, designated with a capital C. The unit of measurement for capacitance is the farad, labeled with a capital F. The farad is much too large a unit of capacitance for practical electrical circuits. Because of this, the microfarad is used, often abbreviated mu capital F. A microfarad is equal to 1/1,000,000th of a farad. Another common unit of measurement for capacitance is the picofarad, abbreviated lowercase p, capital F. This unit, in effect, is a microfarad, or 1/1,000,000th of a farad.
Stop the program and complete activity number 2. When finished, continue watching the program.
It's important that you become familiar with these units of measurement for your future work with capacitors. Let's look at the second important device, inductors.
Like capacitors, inductors are widely used in electronic systems. Inductors come in many shapes and sizes. They are sometimes referred to as coils or chokes.
But regardless of the descriptive term used, an inductor is simply a length of conductive wire that is wound into a coil. Let's examine an inductor's basic operation.
In the previous discussion, you saw how a capacitor stores an electrical energy in the dielectric. An inductor also stores electrical energy, but in a different way. Remember that when current travels through a conductor, an electromagnetic field forms around it. It is within the field that an inductor stores electrical energy. This property is called self-inductance, but is usually referred to as simply inductance. The symbol for inductance is a capital letter L.
Let's examine how an inductor works using this DC circuit. When current flows, a magnetic field is established around the coil. An increase in current expands the field, while a decrease in current reduces the field. In other words, a changing current produces a changing electromagnetic field around the inductor. This changing magnetic field, in turn, induces a voltage across the coil. The polarity of this induced voltage is such that it opposes changes in the magnitude of the current. This self-induced voltage created is referred to as a counter-electromotive force, or CEMF. It's important to realize that the magnetic field will only change while the current is changing. Once the value of the current is established in a DC circuit, the CEMF will stop being induced, and the inductor will behave as a resistor, equal to the resistance of the wire out of which the inductor is made.
Although the explanation so far has involved a DC circuit, the operation of inductors relies on the fact that there is a varying voltage or current present as found in AC. Let's take a closer look.
During the first quarter cycle, the increasing voltage of the AC source produces an expanding electromagnetic field around the coil. This, in turn, induces a voltage within the coil of the same magnitude as the source voltage. Current flows through the circuit in the direction shown. During this first quarter cycle, the inductor is drawing energy from the source. During the second quarter cycle, the source voltage drops off. As this happens, the magnetic field around the inductor collapses, inducing a counter EMF and returning energy to the circuit. The current flows in the direction shown. Between 180 and 270 degrees, this same process is repeated, but with opposite polarities. The increasingly negative source voltage results in an induced counter EMF whose polarity opposes the increase in current. This is because it takes time for the inductor to build up its magnetic field. But once again, during the final quarter cycle, the magnetic field collapses, inducing a CEMF which will oppose the change in current. The inductor returns energy to the circuit to accomplish this. To summarize, the inductor alternately draws energy from the source and then returns the energy that has been stored in its electromagnetic field back to the source twice each cycle of AC. Since the net energy drawn is zero, the power consumed by the inductor in this circuit is zero.
Just as capacitors can have different types of dielectrics, inductors can have different types of cores. Don't forget that the strength of a magnetic field depends on the type of core material used.
The type inductor symbolized on the schematic so far has been for an air core inductor. Some applications require an iron core inductor, which is schematically represented by a coil symbol with two lines next to it indicating the presence of an iron core. The schematic symbol for a variable inductor has an arrow through it. This type has a movable metal core. The base unit of measurement for inductance is the Henry, abbreviated with a capital H. An inductance of 5 henries would be written L equals 5H. The Henry is a large unit of measurement. For many practical applications, 2 smaller units are employed. One is the millihenry, abbreviated with a lowercase m and a capital H. A millihenry equals 1,000th of a henry. The other is the microhenry, abbreviated mu capital H. A microhenry is equal to 1/1,000,000th of a henry.
Stop the program and complete activity number 3. When finished, continue watching the program.
While some of the important characteristics of inductors have been presented, there are many more principles which govern their operation and establish their usefulness.
You'll be introduced to the most important of these principles, reactance, in the next video. You can use the information just presented about inductors to understand the operation of a third and final electrical component that finds its usage in AC circuits, the transformer. A transformer is a special type of inductor whose features make it an indispensable component in many electric and electronic circuits. Like capacitors and inductors, transformers are widely used in electronic circuits and communication applications, in addition to electric power circuits. Let's examine the basic operation of a transformer.
You've learned that when AC flows through a coil, a changing magnetic field is generated around the coil. A transformer is made up of 2 coils in close proximity. If the magnetic field generated by the first coil cuts through the turns of a second coil, an electromagnetic force will be induced in the second coil. This action is known as mutual induction. A transformer only transfers electrical energy from one coil to another by means of a changing magnetic field. Recall that since the magnetic field eventually stops changing in a DC circuit, transformer action cannot take place. Because of this, transformers cannot be used for DC.
Let's take a closer look at how a transformer is constructed.
As the cover is removed from this transformer, you can see the individual coils. Although they are wound very close together, they are neither physically nor electrically connected. They are electromagnetically coupled. The coil to which the AC voltage source is applied is called the primary, identified with the capital letter P. It generates a varying magnetic field, which cuts through the turns of the other coil called the secondary, abbreviated as capital S, and induces a voltage in it. Assuming that all the magnetic lines of force from the primary cut through all the turns of the secondary, the voltage induced in the secondary will depend on the ratio of the number of turns of wire in the secondary winding to that of the primary. This ratio is referred to as the turns ratio of the transformer. This can be stated as the voltage E of the secondary divided by the voltage of the primary equals the number of turns N in the secondary divided by the number of turns in the primary. For example, there are 250 turns on the primary and 500 turns on the secondary. If the primary voltage E sub P is 120 volts AC, what is the secondary voltage E sub S? Rearrange the equation to solve for E sub S equals the number of turns in the secondary divided by the number of turns in the primary times the voltage of the primary. Substituting the values, the voltage of the secondary equals 500 turns divided by 250 turns multiplied by 120 volts. Therefore, the secondary voltage equals 240 volts. From this example, you can see that if there are more turns in the secondary than the primary, then the secondary voltage will be greater or will be stepped up. On the other hand, if the number of turns in the secondary is less than that of the primary, then the voltage will be smaller or stepped down.
Special care must be taken when wiring the transformer into a circuit. If the secondary and primary connections are reversed, severe damage may result. The primary and secondary connections are indicated by markings or by means of a color code. Be sure you know which is which. While the transformer may serve to either step up or step down the voltage between the primary and secondary coils, the actual power that is transmitted from primary to secondary is virtually the same, except for some minor losses with the transformer windings and core.
That is, the purpose of the transformer is to transfer electrical power from one coil to another by electromagnetic induction. It cannot generate or amplify power. Although transformers are not 100% efficient, they are very nearly so. For practical purposes, they are considered 100% efficient. Therefore, the power output equals the power input.
Since the input of the transformer is the primary and the output is the secondary, the relationship becomes the secondary power is equal to the primary power. Since power equals voltage times current, then E sub P times I sub P represents the primary power, and E sub S times I sub S represents the secondary power. If, for example, the primary voltage is 50 volts and the primary current is 2 amperes, then the input power is 100 watts. If the secondary voltage is twice as much as the primary, or 100 volts, then the secondary current must be half the primary current in order to make both sides of the equation equal to 100 watts. The primary current in this example is 2 amperes, so the secondary current must be 1 ampere. So a step-up transformer produces an increase in voltage and a decrease in current, while a step-down transformer produces a decrease in voltage with a corresponding increase in current.
Stop the program and complete activity number 4. When finished, continue watching the program.
Let's stop here and review what you've been shown.
In this video, you've been introduced to 3 important devices that depend on the changing voltage and current of AC to work at their full potential.
You saw how capacitors store electrical energy in a dielectric and how they will charge and discharge twice during each cycle of AC.
You were also introduced to inductors, which can be thought of as storing electrical energy in an electromagnetic field. The electromagnetic field will expand twice during each cycle of AC and collapse twice, sending energy into the circuit.
Finally, you were introduced to transformers which utilize properties of induction between 2 coils to either step up or step down voltage.
A great deal of information has been presented in this video. It's a good idea to view it again. In the next video, the AC fundamental of reactance will be explored, both with capacitors and inductors.